Hello, everybody. Thank you for having me here. Again, I've been part of the Symposium committee before, so it's nice to be up here presenting, giving a talk, and representing the sorghum breeding program here. I'm just going to give a quick overview about our implementation of genomic selection and what that's looked like in my time in the program, given the particular training set that I have. So I'll be talking about genomic prediction in the context of Texas A&M's grain sorghum hybrids. I am in the Department of Soil and Crop Sciences. This is the quick overview of my talk. I'll give you an introduction, make sure we're on the same page, breeze through materials and methods, and hopefully show you some predictions at the end for grain yield mostly, although we are doing this for every single trait that we capture, including some grain quality and root traits as of late. So just to make sure we're all introduced, this is grain sorghum. We're talking about sorghum bicolor. It's the 5th most important cereal crop in the world, as sorghum breeders like to say. It's produced across more than 40 million hectares globally. It's a self-pollinated diploid, 2n equals 20. It does do some outcrossing. It's a C4 grass, so it's highly photosynthetic efficiency is really high. And the factors that contribute to its success all over the world, and especially here in the US, is its drought tolerance, resilience to poor soils, the morphological variation that contribute to its many end uses. But today we're just talking about one end use. It's just grain sorghum. And that production happens primarily in Kansas as a hybrid crop. Kansas is the biggest producing state. But Texas is number 2. And Texas is a really big state, so we have a lot of geographical separation between the mega environments that are going on. So the biggest mega environment is up here, Kansas and the Texas Panhandle. But today I'll be talking about the Central and South Texas production region, which is a totally separate, distinct production environment. And we kind of lump those together when we talk about sorghum breeding. And sorghum breeding, because it's happening in these geographies, we're facing a lot of climate challenges, low water resources. The aquifers are drying up in the Panhandle. And there's not a lot of water available in the state to begin with. But we also have high heat, poor soils. It's not a good equation for us as breeders, but I guess it is job security, so we do have to drive genetic gain anyways. But we have seen a lot of our yield trends kind of stagnate here in the United States. So it's kind of the impetus for why we're switching to genomic selection, or everybody switching to genomic selection also. But that's kind of what we're doing. So today I'm here to talk about our training set development. So this is one of the first training sets we put together in our sorghum breeding program. And that's just for everybody who's kind of new to genomic selection, is where you set aside a set of germplasm, you genotype and phenotype, make statistical associations, and then you can evaluate that on everything else that you can only genotype and you don't have the money and resources to phenotype as well. So with that, I'm applying these models to all of these traits of interest, like I mentioned. But today I'll mostly just be talking about grain yield for the sake of time. We do have NIR traits, like Dr. Diepenbrock was talking about, for grain quality as well, that I'll quickly mention, but I'll go ahead and dive into materials and methods right away. So the set that I'm working with consists of 48 males and 46 females. We cross those in attempting a factorial. It's a partial factorial. These are elite inbred lines that our program had already evaluated prior to me being here. And so we know they're high-performing lines. We also threw in some K-State lines and Nebraska lines in there. But the majority, they're all either released from Texas A&M or they're late stage in the evaluation process. So these inbreds were all genotyped using a genotyping by sequencing platform that the Kleins actually developed and conducted here at Texas A&M, the genomics service here. We actually got 43,000 SNPs out of that, so that's what we're using to build our genomic relationship matrices. And then this is a depiction of what that factorial looks like. If you plot all of the males along the x-axis, all the females along the y-axis, that's 2,208 possible combinations along that grid. We're never going to make that many hybrids and evaluate them all, so that's why we need genomic selection. But for my project in 2018, they set out to make those hybrid test crosses, and they made the blue squares and the green triangle. So all those intersections, you'll see 200 blue squares, 200 green triangles. And so those are the two sets of hybrids that we initially evaluated in 2019 and 2020. And then we actually we had the GBS data, developed the genomic prediction model, wanted to see how good it was, then went back in 2022 and remade some of the ones that we didn't get to see. And with the goal of making the top 20%, the bottom 20%, and then some of the median percentile hybrids along the ranking of that genomically predicted ranks. And so we have 3 different hybrid sets, so the first wave and the second wave. So the first wave, those 2 trials were planted across 4 environments in Central and South Texas. So College Station is where we're located right now. Both years that got both sets. The first year in 2019, Taft got the green set, and then in 2020, Lyford got the blue set. And so those were RCBDs, 2 reps per location. And then the following year, or the following wave of hybrid evaluations, I should say, were in 2023, and those were 4 environments across these 4 locations, still focused on Central and South Texas, and still looking at an RCBD with 2 reps per location. And I should also mention that we phenotyped the inbreds for grain yield, which we don't normally do, but to arrive at questions of heterosis and some other things, we wanted to go ahead and plant these out. So in 2020, we decided to do that in Central and South Texas in College Station and Lyford. So we do have inbred data on those parents as well. And the statistical methods that I'll mention, I just have to, I guess, thank the creators of RRBLUP and the BGLR package, and as of late, the SKM package, and then EnviroType as well. That's kind of the workhorses for these models that I'm about to show. But first, you probably want to see the quality of the data across these environments. What am I actually trying to predict? These are the spreads of those environments with the first wave on the left and the latter wave on the right. That's the distribution. We have decent repeatabilities and CVs for all of our locations, some more informative than others. 2020 College Station was a really good environment. Everything kind of performed very similarly. So that does throw some wrenches in our prediction abilities, but we still, like I said, still were able to make prediction models about it. And in the first wave of our hybrid evaluations, we actually made prediction accuracies for all of our traits. Grain yield being the poorest predicted trait, obviously. But here I'm showing you what it looks like to model additive traits in the blue model, additive and dominance in the orange, and both in a Bayesian way, and then the gray is the blue model's RRBLUP counterpart. So we do have a prediction accuracy hovering around 0.25 for grain yield. And so I guess my question or my charge for my degree and my projects is to see how we can kind of bump that prediction accuracy up a little higher. And so there's a lot of different approaches and a lot of different statistical methods that we can try. So I'm here just showing you a few more, and the incorporation of more terms into the model as EnviroTyping has become a thing. We've been able to include the envirotypic covariates as a matrix here with the W matrix. So all of the models, I should have put one on here that didn't have that, so excuse me, but they all have that. They all have the genetic effects of the male, the female, the hybrid, and then you can see model 3, we start adding some G by E terms, so male by environment, female by environment. And then the last model is the inbred covariates included as a fixed effect. So like I mentioned, we had inbred phenotypic data, so why not try to include that to see if it's adding to our predictive capabilities. It does so very, very slightly, so we're talking about like 0.01, 0.02, but I've never found a situation where it didn't give us that 0.01 to 0.2 increase, so is it really that beneficial? I'm not so sure, but if you have it, why not include it anyways, especially for these models. I've also not seen anything that's really beaten the GBLUP, the Bayesian GBLUP model, or the RRBLUP by a great extent. We're still hovering around 0.25, and we're driving closer to 0.3 for grain yield with some of the incorporation of these terms. But this is kind of where we're at for grain yield, and there's a lot more statistical models that we can show. But you guys are probably more interested in, is this actually useful for our breeding program as it stands, because 0.25 is not a super high correlation or a super high predictability. But we do actually have a small case study here to show you guys. Like I mentioned, that later wave of hybrids was specifically designed to be the top, the bottom, and median percentiles of what the prediction models would say. And so we do have a nice look into the actual observed phenotypes versus the predicted phenotypes from our initial models. And I'm happy to say that the correlation between our predictions and then our actual blues after looking at those is actually 0.62. So this is kind of how we're implementing this in our program. Obviously, it's helping us throw away some of the bad stuff, which is always useful, still saving us resources. and making things more efficient in that sense. Yeah, this is kind of like what we're trying to get at. And so it saved our group some time and effort, and that's always good because these are very hardworking people, and they have helped me throughout my time here. So thank you to everybody in the Sorghumville community and everybody here at Texas A&M that's been part of my education journey. So I'll wrap up there and answer any questions you guys might have.
We have time for about 2 questions.
So you mentioned that you're kind of floating around that 0.3 for predictive ability for grain yield. Is it different if you are looking at the predictive ability of poor grain yield? You mentioned you're pretty good at isolating the ones from that bottom 20%. Is it worthwhile to just pursue isolating the bad ones to then never have to phenotype, or is it equal in labor?
Well, if we start including the bad ones, I think they will string our points out along a nicer line, and so we'd get higher prediction correlations. But then what's the actual like our breeding, we're trying to predict the best, and so we have to change our training set and update our training set to, it'll always have some bad ones to really capture that variation, I think. Does that answer your question, or is there more? Okay. Any other questions? Thank you.